Day 15 of 90 in the Rust Challenge, and today we kill copy-paste forever. You've got two functions, parse_int and parse_float, that are byte for byte identical except for one type. You know there's a better way, but the moment you reach for generics, the compiler throws a wall of trait-bound errors and you freeze. By the end of these 5 minutes, you'll write generic code that compiles, and you'll actually understand what those error messages are asking for. Here's the pain. You write fn parse_int, str, result e32, underscore and then fn parse_float, str, result 64, underscore. Same body, same logic, two functions. Every new type means another copy. Generics fix this by replacing the concrete type with a placeholder, we call it t. So fn parse t, str, result t, err. One function, any type. Beautiful, except this won't compile yet, and the compiler is about to tell us exactly why. Run cargo build and you get error, no method named parse found for type t, and the trait bound t, from str is not satisfied. Read that out loud with me. The compiler is saying, you promised t can be parsed from a string, but you never told me that's true for every t, that's the whole game. A trait bound is a promise. Right now t could be anything, a socket, a vector, and you can't parse those from text. So we add the bound. Fn parse t, from str, str, result t, err. That t, from str means t must implement from str. Now the compiler knows .parse exists, and t-err becomes a real associated type. Build it. It compiles. And here's the magic, call it with parse u32, \42 \, then parse f64, \3.14 \, then your own custom struct that implements from str. Same function, 3 types, 0 duplication. The compiler does the copy-paste for you faster and safer. Why no runtime cost? Monomorphization. At each call site, Rust stamps out a specialized concrete version, one for U32, one for F64, at compile time. There's no boxing, no lookup, no overhead. The generic is a template, the binary holds real specialized functions. This is why the standard libraries vect and option-t are generic and still blazing fast. You get reuse in your source and specialization in your machine code. Let's escalate. Real network service, a logging helper that serializes a payload and prints it. You need two capabilities, so you stack bounds with a plus, fn log_event t, serialize plus debug, payload, t. T must implement both serialize and debug. When bounds pile up and the signature gets noisy, switch to a where clause, fn log_event t, payload, t, where t, serialize plus debug. Identical meaning, cleaner read. That's your translation rule. Every compiler complaint about a missing bound becomes a line in your where clause. Now the decision that trips everyone up, generics versus dyne trait. Generics give you static dispatch, the type is known at compile time, monomorphized, zero cost, but the binary grows and every t is fixed at the call site. Dyne trait, like Boxton's serialize, gives dynamic dispatch one function, a table lookup at runtime, slightly slower, but you can hold a mixed collection of different types behind one interface. Rule of thumb, reach for generics by default, reach for dyne when you need a heterogeneous collection or you want to shrink compile output. One design tip that pays off in CLI tools, put bounds only where you need them. A ring buffer t struct needs no bounds at all to store items, but the method that prints them can require where t, display on just that method, not the whole struct. Per method bounds keep your types flexible and your constraints honest. Don't over-constrain at the top. Day 15 done. The takeaway, a trait bound isn't a restriction, it's the contract that makes generality safe and free. When the compiler asks for a bound, it's telling you exactly what promise your code depends on. Add it, and monomorphization handles the rest. Tomorrow we go deeper into traits themselves. Subscribe for day 16, we're just getting started.